Hi, everyone. As we take a step closer to the Earth, we spent the last lecture taking a look at the universe and the solar system, and then the whole point of this lecture series is going to be dealing specifically with the Earth. So let's take a look at some things that are specific to the Earth that we should need to know. The Earth is the third planet from the Sun. It is 150 million kilometers from the Sun. It takes 365 and a quarter days for it to completely go on one revolution around the Sun, and it has a 24-hour rotational time, meaning that it takes 24 hours to rotate on its axis. Our axial tilt is 23.45 degrees. It is the axial tilt that gives us our seasons. And for a reminder of what's going on with our seasons and how the axial tilt does that, I refer you back to the solar system lecture. So, in the last lecture, we talked about the formation of the solar system and the fact that the whole solar system itself began as a nebula. So we end up with the gases that are moving around as a result of a disturbance, and you end up with all of the more dense materials moving towards the center, and then along the accretion disk you have gases and materials condensing to form planets. Well, the Earth itself, we have a hot ball of gases with our less dense material floating up towards the surface, cooling and solidifying, and that becoming our continental masses. And then all of the denser materials, the metals, the iron, the nickel, moving towards the core and forming the core of the Earth itself. There would have been a great deal of water vapor involved in this, and as that, the water vapor was released from the crust and carbon dioxide, it would have formed dense clouds and it would rain for millions of years, actually, forming all of our lakes and oceans. If we take a look at the Earth's internal structure, the Earth is made of three primary zones: the crust, which is the outer shell, the mantle, which is much thicker than the crust, and below the crust, some of which is solid and some of which is more fluid or plastic. Not plastic like actual plastics, but plastic as in moldable. And then the core itself, which is made up of two parts: the outer core, which is liquid, and then the solid inner core. So if we just take a look at the crust is a layer of rock that covers the entire surface. And this, when I say crust, we're talking about all of the continents plus what is beneath the water in the oceans, which are oceanic crust. So if you removed all the water from the surface of the Earth, you would see continental crust and you would see oceanic crust forming the crust, the entire crust of the Earth. Oceanic crust is thinner than continental crust, and it's made of basaltic rock and it's quite dense. The continental crust is made of granite, and it is much less dense than oceanic crust. And here's a chart that has an actual comparison. Oceanic crust tends to be much younger than continental crust because it's constantly being recycled, being thrust down into the mantle and through volcanism coming back up. And then also you have new oceanic crust constantly being formed at like the mid-Atlantic ridge and whatnot like that. So most oceanic crust is far younger than continental crust. And in this diagram, you can see that in the areas where we have continental crust, picture like mountains and whatnot like that, that the crust extends below the surface as well. So you have, it's much thicker. So as you have thickness going up, you also have thickness coming down. And this is a concept called isostasy, where it reaches an equilibrium point where all of the crust is essentially floating on top of the mantle. Nothing is floating in the ocean. It's floating, they're floating on that essentially liquefied rock, which is the mantle. And the upper part of the mantle itself is more solid, and that's why we call the upper part of the mantle plus the crust itself, we refer to that as lithosphere, solid. So the mantle is a thick part of the Earth between the crust and the core, and it takes up about 80% of the Earth's volume. So most of the Earth is made up of this mantle substances, and it accounts for 2/3 of the Earth's mass, composed mostly of olivine, and then you have ferromagnesian silicate, which means it's a lot of iron, magnesium, silicon, and oxygen. Then we have the core. The core is the center part of the Earth, makes up about 15% of the volume, 1/3 of the Earth's mass, and it has two parts, the liquid outer core and the solid inner core. So how would we know this? We know this because of the fact that we know think back to what we have talked about with waves. Waves change speed and thereby refract when they go through substances and then when they go through different substances. So whenever there is an earthquake on the Earth's surface, we can measure seismic waves actually going through the Earth. And we can map out, as if you put the Earth in a big sonogram, we could literally map out the densities of the materials going through the Earth. And so we know that there is a liquid part of the core. So we know that there is a liquid part of the core as a result of that. Plus, some seismic waves will not go through liquid at all, and so it creates a shadow zone on the opposite side of the Earth. And so we can tell not only the kinds of what densities we have, that is whether it's a liquid or a solid, but we can also tell about how big it is based on these shadows. So that's how we know. Now, we didn't sit around and just make that up. That is actually a measurement that we have. So in looking at a little bit more detailed, what I just said a few minutes ago with the crust itself and the uppermost part of the mantle, it's more solid. Obviously the crust is solid, and then the upper part of the mantle is solid as well. And we refer to that solid part as lithosphere. Okay, we refer to that solid part as lithosphere. Below the lithosphere, we have the more liquid part of the mantle. It's much more fluid, and we refer to that as asthenosphere. So the asthenosphere is a thin, hot layer that's more elastic, semi-liquid layer of the upper mantle, and the lithosphere is the solid layer above the asthenosphere, which includes the entire crust plus the upper part of the mantle, and it's made up of rigid plates that are floating on the mantle. And these would be our tectonic plates. The molten core contains mostly heavy elements, iron and nickel. And so the thin crust part of the Earth is made of much lighter elements. 8 elements make up about almost 99% of the Earth's crust, and these are rocks and minerals. So if we take a look, you can take a look at the Earth's crust up at the top, and what sticks out in your mind? That oxygen is far and away the most abundant element in the Earth's crust. And then the next one is silicon. Well, that makes sense since most of the Earth's crust are made of silicates, which are silicon and oxygen. And if we look at the whole Earth, which includes the mantle and the core, now we start to look and see that iron is the most common element, and then oxygen and silicon. So those plates that are part of the lithosphere are known to move, and this is called plate tectonics, the theory of plate tectonics. And so these are floating up on top of the asthenosphere, and they move because of the fact that you have these massive convection currents. And we've already looked at convection. We know how a convection current works by uneven heating inside a fluid. Well, if the uneven heating in the fluid is working, then what you have is you have these currents, these convection currents that are going in the mantle. Well, the Earth's crust and the top part of the mantle, which is the solid part, the lithosphere, these things are floating around on the asthenosphere, and they're moving because of convection currents. And so we know that the continents drift as a result of floating around on top of the asthenosphere. So they will move around, and that moving around and where you have borders between the plates, this is where we have our seismic activity. And it's also where plate boundaries meet. This is where part of the crust is thrust down into the mantle to be recycled, or part of the crust is pushed up over another part of the crust and you get mountains. So this is where we get so much of our geology from. And if we take a look at the Earth's plates, the top picture points out to you that essentially what the Earth looks like right now, but you can see, for instance, that South America would kind of fit right into Africa. And we know that at one point in time, all of the Earth's land masses were together as one landmass called Pangaea, which literally means all land. And we know this, we call this the concept of continental drift. So the lithosphere has plate boundaries, and the basic. So here are the basics of plate tectonics. The lithosphere is broken into fairly rigid plates, and these plates move sitting up on top of the asthenosphere. Earthquakes, volcanoes, and other rapid changes in the Earth's crust happen most often at those plate edges. If we were to look at the edge of the Pacific plate, where the Pacific plate comes into contact with the North American plate and the Eurasian plate and whatnot like that, what we're going to see is a ring of volcanoes that goes all the way around the Pacific Ocean. This is referred to as the Ring of Fire, and so we see that most volcanoes and most earthquakes and whatnot like that happen at plate boundaries. So there are three types of plate motions. They can diverge, meaning they're moving apart. This is what's happening at the Mid-Atlantic Ridge, where the plate, the North American plate and the European plate or the Eurasian plate are moving apart from each other. Convergent boundaries, where plates come together, and then transform boundaries, where they are moving side to side. The transform boundary is what's happening between the Pacific plate and the North American plate on the side over in California. That's where you get the San Andreas Fault. That's a transform boundary where they're moving side to side. And here we are looking at the plates all together. So you can see the Pacific plate here, and all surrounding the Pacific plate, this is where we're going to have a whole bunch of volcanoes. So most volcanoes are going to happen in this circle right here. So one of the things that you could do if you were teaching your class about, and it was an earth science class, so usually that's in the 6th grade, is you could make this into a puzzle. And so you could outline, you could get this map and cut it out and have students put it together, and then you could actually see how each one of the continents fits on that particular plate. Like the North American plate includes all of North America, and then the Atlantic Ocean almost all the way halfway, and that where the North American plate comes together with the Eurasian plate and the African plate. This is where we have the Mid-Atlantic Ridge right here. So a divergent plate boundary is when you have magma coming up from the asthenosphere and it's pushing the plate apart. And as new magma comes in and pushes the plate apart, you get new land, new crust right here. So remember what I said a little while ago, that oceanic crust is much younger than continental crust. Well, this is showing you exactly why that is. This would be what's going on, like I said, in the Mid-Atlantic Ridge, where you've got new crust is constantly being formed and it's pushing both sides away from each other. So what does that mean? It means that North America and the Eurasian plate and African plate are literally moving away from each other. So the Atlantic Ocean is getting larger. So divergent boundaries occur between two plates that are moving away from each other. Molten material from the mantle rises and fills the fissure and solidifies and continues to push things away. This creates new crust. and typically it's accompanied by volcanic activity, and the Mid-Atlantic Ridge is an example. Convergent boundaries is just the opposite. When two plates move towards each other, old crust is destroyed in the process. This is called a subduction zone. Now, this is what happens when two plates come together. One might slide or is subducted underneath the other. Okay, this is going to create valleys, or it's going to create trenches underneath the ocean. And so as where one bit of crust is being thrust up underneath another piece of crust. If you have two continental crusts coming together, then they're going to push in such a way that they kind of smush and go up and down, and there you end up with mountains. So the subduction zone is where one crust is subducted or sinks up underneath the other. The subducted material melts and joins the mantle. This also creates a great deal of heat, which ultimately ends up in volcanism a little ways away from where it was subducted. So we could have converging continental and oceanic plates, converging oceanic plates, and then converging continental plates. Ocean continental convergence. Oceanic crust is definitely more dense than continental crust. So if this occurs, then what's going to happen is the continental crust is going to move up on top of the oceanic crust. So you're going to end up with you could end up with a trench, you could end up with earthquakes and volcanic mountains. The South American plate and the Nazca plate are a good example of this. And so this happens and it looks something like this, where the oceanic plate is more dense, and so it is going up underneath the continental crust. As it goes deeper, it melts and melts and it gets hotter. Hot things rise, convection, and so what you end up with is volcanism, where it has risen right here. So you end up with volcanic mountains that resulted from this continental crust. So all of this magma that's forming these mountains right here, volcanic mountains, originated with this oceanic crust. An ocean-ocean convergence. This is going to lead to an underwater trench created by the subduction zone, and this gives us those areas up underneath the ocean where it is way deeper than any other part of the ocean. And it still results, you could possibly still have volcanism, which could end up with volcanic mountains in the ocean, which are islands. So you end up with volcanic islands. So here's one bit of oceanic crust going underneath other oceanic crust, again melts, and as the volcanism happens, you end up with island. And that's how we end up typically with islands that are either in an arc or in a straight line in the middle of the ocean. So this is associated with volcanoes. We have island arcs where the oceanic crust is melted and then subducted and then rises, giving rise to these volcanic islands. Now, that's not like Hawaii. Hawaii actually is a place in the middle of the Pacific Plate where we happen to have a hot spot. And so it creates this chain of volcanic islands. Continent-continent convergence. Since continental crust is less dense than oceanic crust, but you've got two that are coming together, neither of them is going to just readily go up underneath the other one. So what happens is the two plates kind of pile up on each other, creating, kind of deforming the crust and creating these really, really tall mountains like the Tibetan Plateau or the Himalayan mountains. This would be like where, Mount Everest and whatnot. So they kind of squish together and deform, and so what you end up with are these massively tall mountains that are still growing, in fact. Transform boundaries are plate boundaries that slide next to each other. So the crust oftentimes is neither created nor destroyed in this process, but what happens is it does create a great deal of tension and then sliding, which is an earthquake. So irregularities in this movement along the boundary with sudden jerks creates an earthquake. An example, like I said, is the San Andreas Fault. The San Andreas Fault is where the Pacific Plate and the North American Plate come together. All right, so another Earth process is something called weathering. We often hear weathering and erosion together. Well, and they often do happen together. Weathering is what happens when materials are broken down. So they break up, they crumble, and they are destroyed, and become where solid rock is destroyed to become smaller rock. Okay, these could be physical processes, which is rocks crashing up against one another. It could be water freezing inside the rock and cracking it and whatnot like that, or it could be a chemical process of weathering, such as if you've got acidic some sort of acid that's on carbonates and whatnot like that. It could be biological processes where you've got things like lichens and whatnot that are physically breaking up stone. This weathering contributes to the rock cycle because the rock cycle happens when you have rock that's weathering away and then it reforms into other rocks. But the weathering is simply the breaking down of big rocks into little rocks, essentially. Weathering contributes to the formation of soils. When you have succession, we've already talked about succession and the fact that when you start with bare volcanic rock, it ultimately becomes soil. Well, that's a result of weathering. Movement of rock over other rocks tends to weather a surface. So that's weathering. Erosion, then, which is always working in pairs with weathering, is the process of physically removing those weathered minerals or the weathered particles, just moving them someplace else. So weathering is breaking it down. Erosion is moving it to a different place. So when we have mechanical weathering, this is the physical breakup of rocks. Okay, the physical breakup of rocks without any sort of chemical changes. This could happen by way of frost or trees splitting rocks apart, exfoliation, the layers of rock coming apart, reduced pressure effect with fractures causing expansion of underlying rock. So rock expands and contracts, and so you end up with this fracturing. So that's mechanical weathering. So here's some examples here. So when water freezes, it expands, and so it will crack off part of the rock. So this is mechanical weathering. Chemical weathering, on the other hand, is when you have deposits of minerals by chemical actions. You might have oxidation, which is the reaction when you've got elements that are reacting with oxygen, and literally it means that you are adding electrons to something. Produces red iron oxides. Well, that's the product of, essentially that's rusting when something is combined with oxygen. Carbonation, when carbonic acid, which is CO2, CO2 is present, and what it does is it will dissolve carbonates, which is a limestone, so it will dissolve limestones. You may have hydration, which is where the water itself will literally dissolve substances that are present in the rocks. So you could have this chemical weathering. And there are all sorts of examples of chemical weathering. Erosion. Erosion is when weathered material is moved from one place to another. So we might have mass movement. You might have a landslide, rock slides, that sort of thing. Erosion can be caused directly by gravity. Okay, if it's slow, then you might have soil creep down a mountain, okay, and that sort of thing. Or you might have a landslide, which is acting by gravity, but it's acting very rapidly. And so, or you may have wind erosion, water erosion. When water flows past weathered material, it's going to carry that weathered material away. Same thing with wind. So here's soil moving down the mountain. Running water, I just said running water could be a wonderful method for erosion, because as water runs, it's going to take weathered material with it along with dissolved material. So anytime water runs, and you've probably seen this around your house and whatnot like that, if it rains, and if you don't have a trenching system or a system of, you know, your gutters outside aren't working too well, then running water, and this is going to take a lot of your soil, and it's going to take it to wherever the water runs to, it's going to take that soil, and that is a clear example of erosion. Deltas happen at the mouths of rivers, where rivers come into contact with the ocean. And it's called a delta because it's a fan that spreads out. Let me see, I've got an image right here. It's a fan that spreads out into a triangle, and a triangle is the Greek letter delta. And so what happens is that as the water is running, you've got this river, and as the water is running down the river, it's going to be carrying a lot of sediments. As it reaches the ocean, it's going to slow down. And as it slows down, it drops these sediments. And so what you end up with is this fan-shaped delta. Glaciers are also agents of erosion. So we don't have a lot of these acting at this moment, but glaciers have throughout Earth's history been big agents of erosion. As glaciers move across an area, they will pick up and carry all sorts of weathered material and dig out lakes and whatnot like that. So you also could end up with glacial valleys, where a glacier has literally cut a valley through a set of mountains. So continental glaciers are glaciers that cover large continents. So like Greenland has a glacier. There's glaciers in North America, up in Canada, like near Whistler, over on the British Columbia side. There are other glaciers. As glaciers move, like I said, they will pick up and carry, and it's like this big, a big smoothing stone moving around. So here's a glacier moving through a mountain valley here. So glacier moving through a mountain valley. Wind is a big agent of erosion. Okay. It has considerably less force than water or ice, but it still moves. And if you've ever been outside at the beach with a big sand where the wind is blowing, then you know how much of an agent of erosion wind can be, because it's going to be blowing sand everywhere. As that wind blows, it's going to pick up the sand and other particles, and as soon as it starts to slow down, though, it will drop whatever it has picked up, which is why dunes in the desert are constantly moving. Dunes in the desert are constantly moving. Abrasion is natural sandblasting. So as wind moves the sand, that sand actually could be another agent of weathering. Deflation is when loose material is picked up and carried away by the wind. So whenever we talk about wind erosion, really we're talking about deflation. So wind-blown deposits, such as dunes, they said this is why the dunes in a desert are constantly moving, because as the wind picks them up, as the wind blows faster, it picks up the particles, and as the wind starts to slow down, it drops the particles. Okay, loess is fine dust that is deposited over a large area. So when you have massive windstorms, you can end up with dust moving vast distances. You can end up with dust that moves vast distances, like from continent to continent. Vast sandstorms in Africa will end up blowing dust all the way over to North America and whatnot. So we'll end up with dust particles from Africa as a result of those dust storms. Folding. Folding takes place when part of the crust starts to come together and it bends. And it's moving slow enough, but with enough pressure to slowly bend part of the crust. And you can see that here, as this would have had pressure coming from both sides, and it literally bends the crust. Okay, we call these folded mountains. So it works something like this. So we have anticlines and synclines. Anticlines is when we have the arch shape of the fold, and synclines are when we have the trough shape. So a syncline would be down here. So anticlines and synclines, part of folded mountains. Faulting. Faulting happens when you've got pressure on two sides of part of the crust, and it literally breaks. And when this breaks, part of the mountain, the part of the crust, if these two things are pushing against each other, towards each other, then one is going to move upward and the other one is going to move downward. We refer to this as a hanging block. The one that's on the top of the crack is referred to as the hanging block wall, or the hanging wall, and the foot wall is on the lower side or on the bottom of the crack. So whichever part of the rock is moving upward, that's the hanging wall, and the foot wall is the part that the hanging wall is moving up and over. And here you can see that. So here's our fault, and so this is our hanging wall over here, and this is our foot wall. Earthquakes. Anytime you have shaking, vibrating in the ground because the ground is moving due to a fault or to where two plates are converging or moving apart or moving transverse to one another, these are earthquakes. And so it results from a sudden release of energy from stress on the rock. So if you have a transform fault here, that there's pressure coming from both directions, then all of a sudden you get a slippage and they move suddenly and rapidly past one another. That releases a great deal of energy, and that would be an earthquake. Most of our earthquakes occur along fault planes. So when one side is displaced in relation to the other. I mean, you literally can have part of the land displaced a good bit past the other, multiple feet. So we have two plates that are pressing tightly against each other. Friction is going to keep them from moving for the most part. But eventually that friction is going to give way, and either both plates or both parts of the crust are going to move, and so one moves really rapidly up and over the other. They're going to move side by side to each other, etc. And when that happens, it's what's called an earthquake. So stress builds up until the friction is no longer strong enough to hold it together, and then the rock snaps apart and that suddenly into a new position, and that's the earthquake. And here you can see that. So if we have part of the land that's being pushed in one direction and it's being pushed in the opposite direction over here, eventually this fault snaps, and so you end up with what was a straight fence, you end up with a curved fence or a broken fence. A tsunami. A tsunami is a very large ocean wave, and it's not like the wind-driven waves that we've looked at before. This is when a massive amount of water has been displaced because of an underwater earthquake, or when a large amount of oceanic crust has either been thrust upward or thrust downward really rapidly. So it's like if you think about just completely displacing an awful lot of water. In fact, most of the things that create artificial waves, most things that create artificial waves in pools and things like that, really that's more like what a tsunami is than like regular waves. Regular waves, like the ones that we surf on and things like that, those are caused by the wind. But when you have a large amount of water that's displaced by something either moving rapidly down into the water column or something moving up in the water column and rapidly displacing a lot of water, or moving across part of the water column, that creates an ocean wave, a tsunami. So earthquakes, landslides, volcanic eruptions, meteoric impact, all of those things will displace a lot of water. And when it displaces a lot of water, that creates a tsunami. And a tsunami could be moving, you can't outrun one. It moves way faster than a regular wind wave. And it could have heights of up to 25 feet or more. Origins of mountains. We've kind of talked about origins of mountains already when we talked about when two plates come together, two continental plates come together and they kind of smush upward. Okay, that typically is called a fault block mountain. And then when you have plates that move slowly and they fold, and we end up with something called folded mountains. So mountains are caused when we have elevated parts of the Earth's crust rising up out of the surrounding surface. So we could have folded mountains, faulting mountains, or volcanic mountains. And actually, we've talked about all three.